Thank you for the introduction. It's a pleasure to be here. So this is joint work with Charles Pfefferman, Sergei Ivanov, Yaroslav Kurilev, and Marty Lasers. So I want to start with a motivating example. Cryo-EM is a method of producing 3D structures of viruses and other large macromolecules. And this involves taking pictures of a large number of molecules embedded in a thin layer of ice. These molecules have random orientation. So what you end up getting is a picture having many different picture of many different molecules having many different orientations. These things are very noisy. And basically, you need to reconstruct the 3D structure from all these noisy images. So why is manifold learning relevant for this? Well, the space of rotations of a 3D molecule is SO3, which is a manifold. And so you can associate these different views of a 3D molecule with points on this manifold. And if you just plot all the images in some high-dimensional space, so suppose these images are 200 by 200 pixel images, these will be 40,000 dimensional space images. And these can be viewed as points in this 40,000 dimensional space. However, they also would naturally tend to lie on, if they were noiseless at least, they would tend to lie on this embedding of SO3 in 40,000 dimensional space. But as I said, there's a lot of noise which we will model by Gaussian, white noise. And so the question is not exactly that of fitting a manifold to points which are noiseless, but rather it's fitting a manifold to points which have additional Gaussian corruptions. So this is a sort of attempt at portraying that. So here we have a torus, and these points don't exactly lie on the torus. They are perturbed so that they lie at some distance away from the torus. And these perturbations are assumed to be Gaussian. So as I mentioned, the natural manifold associated with cryo-EM is SO3. If additionally these images can be perturbed laterally, so you don't know exactly where the molecule is in the picture, then you have these points lying not on SO3, but rather a two-dimensional disk bundle over SO3, which is essentially something like this. So this could be a manifold, and this could be the disk bundle, where around every point on the manifold you have a disk associated. So we would like to infer the manifold from the noisy samples, and that's what this talk is going to be about. But in order to be able to do this, we need to place some restrictions on the manifold M. So this is the case for any such task, such as curve fitting. So the assumptions we'll place are that A, the manifold has no boundary and is d-dimensional and twice continuously differentiable. The reach of the manifold is at least tau. I'll explain what the reach is. And the d-dimensional Hausdorff measure is at most V. So what I mean by the first condition was that if you take this manifold, then there is a ball around every point on this manifold with the following property. I can draw a y-axis and an x-axis. This y-axis will be n minus d-dimensional, and this x-axis will be d-dimensional, such that the intersection of the manifold with this ball is the graph of a twice differentiable function. So locally, it looks like a twice differentiable function. But of course, globally, it might patch up in some complicated way, might curve and so on. Uh, so this is what we mean by the reach of a submanifold. So in the previous thing of lecture of Satya, we saw that this oscillating circle. So that's actually the oscillating circle. It's related to the maximum or the minimum size of an oscillating circle, but it's not exactly that because it encodes some global information as well. So what it does is it's the largest tube you can have around a manifold with the property that the tube does not self-intersect. So if this is the manifold, then so somewhere around this radius, the tube will start developing non-differentiable parts. And that's where you stop and say that you've reached its reach. So you've come to its reach. If you go any further, then you would not have these, these normals would start intersecting basically. And you want to stop before these normals start intersecting. So that's the reach. It's some natural notion of inverse curvature. The smaller the curvature, the larger the reach. For example, a straight line has an infinite reach. And the d-dimensional Hausdorff measure is just the usual d-dimensional volume, but it's been formalized here in terms of the volumes of tubes divided by the cross-sectional area. So you take a limit of the volume of a tube divided by the cross-sectional area as the cross-section tends to 0. So this is going to be the formal statement, formal problem statement. Let x1 to xn be i.i.d. drwas from a measure that is a density corresponding to this Hausdorff measure, and the density lies between rho min and rho max. And then you add Gaussian noise to each of these points from a density that is given like this. So one thing I'd like to point out right away is that although the n only figures in the exponent here, if you pick a random Gaussian from such a distribution, the expected length of that deviation is going to be roughly square root of n times sigma. So it's going to be rather large in high dimensions. So we are going to assume that the sigma is really small, but not small in terms of sigma root n. So n can be extremely large. So n in our setting was 40,000 for the cryo-EM. But d is some notion of effective ambient dimension, which could be much smaller, which I'll come to a little later. So we're going to assume this condition. And under this condition, we want to reconstruct the manifold from the noisy samples. So the first step is a very natural dimension reduction. Basically, you do PCA with sufficiently many dimensions, project your noisy data onto the PCA, and effectively what happens is that the noise just gets attenuated by a large factor, but the manifold being roughly in the span of the PCA is not attenuated, so you recover the manifold more or less. So, so here we are going to be saying that if you project a manifold onto the PCA subspace, something nice happens. So that's what this is saying. So here are some parameters I want. So maybe I'll just point out this, that so this D that I talked about has an intrinsic definition. It does not depend on the ambient dimension n. It depends on the Hausdorff measure of the manifold. It depends on beta, which is related to the reach, and it's related to the intrinsic dimension D. So it is not related to that 40,000 dimensional ambient space. So the lemma is the following. It is that if you take n points, i.i.d. from mu, S be a d-dimensional subspace that minimizes the sum of the squares of the distance to subspace, then the maximum distance of the manifold from the subspace is not too large. So this is the manifold. I'm drawing only a part of it, not the whole manifold. This is what I get when I do PCA. And what I'm saying is that this maximum deviation is not too large. This is not too large. And so what happens is, if I project, something reasonable will happen. So in order to show that when you project something reasonable will happen, you need some facts about the structure of manifolds with a bounded reach. And this is such a statement. What it's saying is that if the reach is tau, then I can take a cylinder of side tau by 8. So this is a quantitative version of what I said here. So I can take a cylinder of side tau by 8 and still get a C2 function. I will not see something like this happening within this region, as long as this cylinder is oriented along the tangent space to one of the points in the manifold. So for a circle, for example, you can say stronger things. It's not tau by 8, but basically something like tau. If you go all the way up till tau, you're going to get this cylinder here. And this whole thing is the graph of a C2 function, except at these points. At these points, the slope is tending to infinity. So let's be slightly less than tau. So as long as you're slightly less than tau, you see it's the graph of a function. But if you go any larger than tau, then you get something like this. And this is not the graph of a function, because this manifold starts curving back. So this is also further saying that the slopes of this manifold form a Lipschitz family. So if you go delta away from this point, the slope is given by 20 delta by tau. So it's a Lipschitz function. That's all this is saying. Yeah. That is matching tau. But the lemma says something weaker. It says that only for tau by. It probably can be strengthened, but we don't need, because we don't care so much about absolute constants. So what this is saying is that if you have any linear subspace near a manifold of reach tau, so you have a manifold of reach tau. Now this has nothing to do with PCA. You take any subspace that has the property that every point on the manifold is near the subspace. Then when you project the manifold onto this linear subspace, you get another manifold, and that manifold will have a good reach. That is what this is saying. It says the reach is at least this quantity, which is some constant times tau, and this will be close to 1 if alpha is very small. So the reason we are doing this is that we don't even want to look at the whole space. The whole space is far too large. We want to do a PCA. We want to project the data onto the PCA subspace, and then we want to do some analysis on that PCA subspace. And what this is saying is that as long as the choices of these things are okay, the reach of the image will be good, and also the other parameters will be good. The other parameters are not so difficult to show. Like volume is good simply because you get some sort of bound in the slopes. If the slopes are good, then the volumes are similar. And the other parameter was dimension, which also follows from similar arguments. So now, what is the algorithm? So the setting we are in is the following. You start with a manifold. You have sample data, you added Gaussian noise. Now these vectors are extremely large. They are of size root n times sigma. But now we have done a PCA, and we have chopped off, and all the noise, random noise, is going to get attenuated to become from square root n sigma to square root d sigma, where this is the effective ambient dimension defined by the dimension of the PCA subspace. Now, once you've done this, this is by design, by assumption, this is small. So now we are not in a setting of large noise. We're in a setting of very small noise. So we are in a setting like this, and we need to fit a manifold to data that looks like this. And so now this is about that. So the basic method is going to be you start fitting disks to the data locally. And then you patch together these disks using the implicit function theorem in some fashion. So what is Hausdorff distance? So Hausdorff distance is a notion of distance between subsets. If you have two sets X and Y, then the Hausdorff distance between X and Y is equal to, let me just draw a picture. So this is X, this is Y. So you take the farthest point here from any point here. So in this case, it'll be something like this distance. You take the farthest point here to any point here. In this case, it'll be this distance. And you take the max of these two. So it becomes 0 if the sets coincide, for example. And what is the idea to pick a disk that is good locally? The basic idea is you pick a d-dimensional basis from the intersection of the point set with a ball. And you take the linear span of that basis, and you intersect that linear span with the ball. So you get a d-dimensional subspace that is an approximation of the tangent space of the manifold. And you take that. And one can show that this does reasonably well in a worst case sense. This is just the algorithm. It's basically just pick faraway points that are all almost orthogonal to each other, take their linear span, and then one can show that in Hausdorff distance, this does not do much worse than the optimal. And by much worse, I mean you gain a factor of d over here. So initially, if the optimal is delta, Hausdorff distance, now the Hausdorff distance becomes d delta. And when I say Hausdorff distance, I mean the Hausdorff distance between the disk and the intersection of the point set x naught with the ball. So for example, if I had points like this, then I'm going to put a disk like this, and the Hausdorff distance is going to be something like this. This is going to be the Hausdorff distance. So that is what we can make small. So now what is the method of patching up? I want to briefly describe the method of patching up. So we got these balls. So there are some conditions on how the balls need to be in relation to each other. I'll not get into that. I'll just state that suppose you have these balls. So they should neither be too close to each other nor should they miss any part of the manifold. So for that you need to enforce certain criteria. But there is this notion of a partition of unity, which is a bump function that looks like this. And what we are going to do is we're going to take functions defined on the different balls and combine them into a single function by doing something like this. Summation alpha I fi of x. So I'm going to do something like this. Summation alpha I fi of x. Alpha I is also a function of x. And what this does is it allows you to smoothly transition from one function to the other. Because they attenuate in this fashion. That's right. It will depend on capital. No. So actually what happens is that it is linear in n. So the thing is, because this is square root n sigma, even if your manifold were inside a unit ball, if you want to reduce the variance by this much, no, it's linear in n. Yeah. Yeah, a large reach. Large reach is better. Yeah. So these things are tailored towards having a large codimension. So if it's a function, then typically you're talking about a function from RD to R. Yeah, I'm talking about a function that is effectively something like RD contained in Rn. So it's a curved embedding, let's say, of RD in Rn. But it could not. It doesn't have to be a RD. It could be some other shape. Sure, you can take a quadratic and embed it. You can take the graph of a quadratic function and embed it in Rn. Yeah, that's a reasonable example. But a low dimensional thing, yeah. No, so the graphs of these functions are manifold, so they would extend. But I'm not concerned with the mapping from the x-axis to the y-axis. I'm concerned with the structure of the points x comma y. So that's the only difference. So it's an intrinsic way of looking at it rather than having a. Yeah. So this is the main thing. So how do we now patch together lots of disks, right? So if you have a number of disks, the method is the following. You first define you define a vector field which is given by pi I of x minus pi. Pi I is the orthogonal projection onto the disk. So you have this disk, you consider the projection onto the ortho complement, and that is pi I. And now you mix these pi i's together, or is that later? No, right now you don't mix pi I together. So pi I times any point here. So you want to get this vector field. So you just pi I times x minus pi. Pi is the center of the disk. So this is a vector field that you get. If this is your disk, then it points away from it everywhere. In all directions, it just points away from it. And it linearly increases in magnitude as you go farther and farther away. So next, we want to mix these things together. So I've got this vector field, I got a similar vector field like this, and you want to mix them together. So you mix them together using these partitions of unity. So you have summation alpha I fi of x. So that is going to be a vector field in the neighborhood of the manifold that we don't really know. It's just a vector field. Now we are going to say that it's a set of all points. We would like to say that it's a set of all points where this vector field is 0. Unfortunately, that is not true because of the misalignment in the disks. So what we will say, however, is if you now project this vector field onto a certain set of planes, you will get a new vector field, and the zeros of that vector field are the manifold. So f of x is the vector field. At every point x, you define a pi x that is obtained by mixing together the different pi I. These pi I are projections onto the ortho complements of the disks, but they change in the position. So how do you mix these together? You like to say it is summation alpha I pi I. Unfortunately, this map is no longer a projection because typically it's got lots of non-zero eigenvalues. So what you have to do is you have to take the large eigenspace of this operator, and that is the pi x. And then we are saying that the manifold is basically the set of points where pi x f of x is equal to 0. Okay, so then one has to say that its reach is good. And the way to do the calculus is to use Cauchy's integral formula for matrices. So then you can write this explicitly as an integral, and you can twice differentiate pi x inside the integral. And so that's what I want to stop with. I just want to say that, so the final lemma states that suppose sigma is small compared to tau, then the reach of M output is at least tau by d to the 4, the intrinsic parameter, not extrinsic parameter. And the distance of the manifold to the true manifold is also controlled, assuming this is controlled. And n does not figure in this. D appears, where d is the effective ambient dimension. So I'll stop with this. Thank you.